Okay, hi everybody. So, the point of these problems, like that are quizzes where you're quizzing yourself on this afterwards, is that there are some things that you should just be really familiar with. Because, like certain examples, like to just really know immediately, harmonic sequence. This is an example that I'm just going to use again and again to test my understanding of concepts. Alternating, prime numbers, geometric sequences, oh my gosh. Those are going to be, well, these are going to be super important, geometric sequences. So anyway, these are good examples. Let's just commit them to our example zoo, our zoo of examples. Okay. So I'll actually do part B first, the alternating harmonic sequence. Xn the harmonic sequence is xn equals 1 over n. So for example, x1 is 1, x2, x3, x4, x5, etc. But here's the formula. Okay, the alternating harmonic sequence will have the same formula, except we want it to start at 1 and then go minus a half, then 1/3, and then minus a fourth, and then 1/5, and then minus a sixth. And so to do that, we're going to put some factor of -1 that either goes -1 plus 1, -1 plus 1. And I guess at n equals 1, we want it to be positive, so let's do n plus 1. And that's a little hard to read, so I'll move this over. In other words, -1 to the n plus 1 times 1 over n. Okay. If you wanted it the other way, then you could do -1 to the n, but then that would be negative plus negative plus negative plus. Either way is fine. But these have to match, right? Your formula should give whatever you write out. Okay, the prime numbers. Well, you can't really do a great formula for this. If you could solve all sorts of problems. But I'd say x sub n is the nth prime number when all primes are listed increasingly. Are listed increasing. I don't know, like what's the first prime? I guess 2, and then 3, and then 5, and then 7. Are these all prime? 9 is not. 11, 13, 17, blah, 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 blah. So I keep going. D. The geometric sequence with fixed parameters. Now, okay, so for any choice of a complex number A and a complex number C, we create what sequence? Well, the nth term is just going to be A times C to the n, where I'm just raising C to the n, and A is just sort of like an overall scaling. You could imagine a sequence that was the other way around, C times A to the n, and that would be fine. That's absolutely fine. We're just naming these whatever we want. In fact, we can choose other names. So let's choose other names. How about, let's this be R for the ratio, and this be B. How about B? B times R to the n. Okay, that looks good. So for example, it would be R to the 1 is just R. And actually, let's start this at n equals 0. So include n equals 0. This will be important for geometric sequences. We actually want to start with 1 times b. Okay, and then b times r, and then br squared, and then br to the third, and then br to the fourth, etc. So each time we're just multiply by r. We just times r. We just times r times r. And in fact, r is sometimes called the common ratio. And this has the name geometric sequence. You're just going to see this throughout your career in math, physics, anything to do with math, really, is this word. So just commit it. This is what people mean. They mean something that looks like this. It's good to know the names of things. Okay. The geometric sequences whose elements are roots of the polynomial z to the k minus 1. Okay, so part E. So what we want is, let's say k equals 5. Okay, then this geometric sequence should start at 1 and then go to this number 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 again and then this one again and then this one again, and each time it's just rotating by the same thing. And so to multiply by a number that'll rotate exactly that amount each time is just actually to multiply by that number. And we call this sort of the first root, I guess the first fifth, the first fifth root of unity. This is very silly, but anyway, and in fact, let me just cross this off so that you're not confused by it. We set r equal to cosine of some amount of 2 pi. I want 1/5 of 2 pi plus I sine of 1/5 of 2 pi. Why? Because that will give me exactly this number. Okay, and that's what we want to do. We just want to rotate around. Each time we're going to multiply by r. And this time we'll start with b equals 1. So what's the sequence we get? Well, first of all, a formula, x to the n is b times r to the n. And this would look like 1 r squared, r to the third, r to the fourth, r to the fifth, r to the sixth, r to the seventh, etc. forever and ever. And in fact, notice that r to the fifth is 1. I have r squared, r to the third, r to the fourth, r to the fifth. That's back at 1. And so if I wanted, I could write a 1 here. Okay, and if I wanted, I could write an r here. And if I wanted, I could write an r squared. So this is also this sequence. Okay, when I choose this value of r. Okay, so in general, for arbitrary k in the integers, set r equal cos 1/k of the way around a circle, 1/k of the way around a circle. Then x to the n equals r to the n gives this special geometric sequence. Geometric sequence. That's it. Okay, so really, that's a good one to know. And you see, it's a special case of geometric sequence to get all these roots over and over again. Okay, but now let's do one where we're on the unit circle again, but they never repeat. So this one repeated. 1 happens infinitely many times. R happens infinitely many times, etc. They repeat. So let's do one that doesn't. This was EF, part F. And in fact, but basically what we have to do is, the fact that this repeated, that this cosine of something, some angle, gave the same thing again, and this sine gave the same thing again, is because we took a fraction of 2 pi. A fraction of 2 pi. So if you think about it, if we took even cosine of a over b times 2 pi, plus I sine of a over b times 2 pi, that will eventually repeat. It will repeat when we do, if this was r, then r to the b, so if for a and b integers, in other words, for any rational number, r to the b equals r to the, is this going to work? R to the 2b equals r to the 3b. Does this make sense? Let's see. Yeah, I think so. Because if we rotate around, yeah, because we're just going to get an extra 2 here, and that's just going to multiply by another 2 times 2 pi, which will give the same value. And over here we'll multiply by 2 times 2 pi and give the same value. So, yeah, so this would not work. This will repeat. Or r to the n will repeat. But if we choose instead, let r equal cosine the square root of 2 times 2 pi plus I times sine the square root of 2 times 2 pi. Then x to the n equals r to the n never repeats. Okay, so it's going to go around the unit circle, and it'll just never repeat. Or it's probably not going to, yeah, I think so. So I'm doing like 1.4 times 2 pi. So like I'm thinking like, oh, I go a whole 2 pi and then another 0.4 of 2 pi. Okay, so maybe I'm actually here. Then I go a whole, so that was, this would, if this is 1, that's equal to r to the 0. Then here's r. Then where is r squared? Well, it goes a whole time 2 pi and then another 0.4 times 2 pi, so here's maybe r to the 3rd. And then I have to go around again by a whole 2 pi and then a 0.4 of 2 pi, so maybe here is r to the 4th. And the claim is, every time, even though we're going to fill in, it will actually never repeat. Because the square root of 2 is not a fraction, since square root of 2 is not a rational number. Okay. Think about that. That's super interesting. Totally not obvious, but you can, if you just keep doing computing more and more of these r to the n's, you'll get a sequence that fills up the unit circle. It fills the unit circle, but never repeats. That's kind of cool. Is that it? Harmonic? Yeah, okay, so, quiz yourself. Do you know what the harmonic sequence is? What the alternating harmonic sequence is? Can you give formulas? Oh yeah, prime numbers, that one not so much. But then geometric sequences. How about a geometric sequence that will repeat and give you the kth roots of unity? And then what about one that never repeats? Yeah. Yeah. Let's look at this. Let's just take this number. I'm going to square it. If this is my number, I want to square it. What do I get? So let's multiply this number by itself. And what we'll get is a cosine of 2 pi over 5 times a cosine of 2 pi over 5. That's from this times this. Okay, there's 3 other terms. We get 4 terms because I have 2 terms here times 2 terms here. So I'll get 2 times 2 is 4 terms. And actually, I'm going to just group them. You see that the I sign and the I sign will multiply and become minus 1 times sine 2 pi over 5 sine 2 pi over 5. Okay, so that's the real part of the number that we get. So let's look at the imaginary part. It'll be an I times a cosine sine, and then an I times a cosine sine. So let's look at that. I get I times, I guess, 2 cosine sines. Okay, so this is the real part. This is the imaginary part. Imaginary part. And yeah, in fact, I mean, you could just write this cos squared. So I guess cosine of 2 pi over 5, the whole thing squared, minus sine times 2 pi over 5, the whole thing squared, is the real part here. And what this is that this is actually equal to the cosine of 2/5 of 2 pi. And this is actually equal to the sine of 2/5 of 2 pi. And that is not obvious. Those are from certain trig identities. But this geometry of the complex numbers eventually will allow us to prove that. Just because if we have the number r, which is here, and it's at an angle of, let's say, 1/5 of 2 pi, then if that's r squared will have twice the angle. R squared has twice the angle. Its angle is 2/5 of 2 pi. And so that's just from geometry. You can just see, we just rotate again by r. But its real component is the cosine of that angle, and its imaginary component is the sine of that angle. But we can also multiply the cos and sine of the original r, which were this real number and this real number. And then we see that the real parts must be the same, equal, and the imaginary parts must be the same, equal. So, yeah, that's interesting. You can discover, if you forget your trig identities, you could remember them by doing this calculation. This is not a part of the problem, but it sort of was secretly a part of the problem because of all these unit circle things.